So, a network of qubits entangled together, just like a quantum computer. Out of that we suspect that space and time might. Brian Cox once said quantum mechanics is deeply weird, but it works. But what if it starts working in ways even physicists can't explain? The Majorana 1000-Qubit quantum chip isn't just breaking computational barriers, it's rewriting the rules of reality itself with qubits that seem to alter the past and anticipate the future and defy the very laws of physics. Are we on the verge of a quantum breakthrough or a scientific reckoning? The development of the Majorana 1000-Qubit quantum chip represents a paradigm shift in computational power and quantum mechanics, designed to overcome decoherence, the Achilles heel of traditional quantum computers. The chip utilizes Majorana fermions, exotic quasiparticles theorized by Ettore Majorana in 1937. These fermions, which are their own antiparticles, provide an innovative foundation for topological qubits, encoding information in a manner that is fundamentally more robust against environmental disturbances. With this breakthrough, researchers anticipated a new era of practical quantum computing capable of revolutionizing fields such as cryptography, drug discovery, material science, and artificial intelligence. Yet, what began as a triumph of engineering has transformed into an enigma. The chip's full-scale deployment has yielded behaviors so anomalous that they challenge our understanding of quantum physics itself. Researchers have observed computational outputs that alter past inputs, qubits maintaining superposition states far beyond predicted limits, and calculations resolving before their conditions were fully defined. These anomalies have ignited debate across the scientific community. Are we witnessing the emergence of a fundamentally new quantum phenomenon, or are these results artifacts of an undiscovered flaw in the system's architecture? To grasp the significance of these anomalies, it is crucial to understand how Majorana fermions function within a quantum computing framework. Unlike conventional qubits, which are highly susceptible to decoherence, Majorana qubits store information non-locally by distributing quantum states across multiple locations in a system. This topological protection makes them inherently resistant to minor perturbations such as temperature fluctuations or electromagnetic interference that typically plague other quantum systems. Theoretically, this non-local encoding could enable quantum computers to perform calculations with unprecedented stability. Unlike classical bits, which exist as either 0 or 1, qubits can exist in a superposition of both states, enabling quantum parallelism. The 1000-qubit expansion was expected to push computational boundaries, allowing for problem-solving capabilities that would dwarf even the most advanced supercomputers today. However, with great computational power comes unforeseen complexities. In the case of the Majorana 1000-qubit chip, these complexities have surpassed expectations in ways that defy standard quantum mechanical interpretations. If you're excited about the future of quantum computing and want to stay ahead of the breakthroughs, hit that subscribe button. We cover the latest in quantum tech, space exploration, and cutting-edge science. And if you found this video interesting, drop a like. It really helps more people discover this content. Unprecedented anomalies and computational deviations from predictability. Since the first full system activation, researchers recorded unexpected quantum behaviors, persistent superposition states. Standard quantum decoherence models predict that superposition states collapse over time due to entanglement with the environment. Yet certain qubits within the Majorana system seem to defy this expectation. The chip remained in superposition orders of magnitude longer than predicted, suggesting a potential violation of the accepted quantum measurement paradigm. Nonlinear output shifts. Initial computation returned expected results, but subsequent analysis showed that previous inputs changed retroactively to align with newer outcomes. These shifts were consistent across multiple trials, challenging the notion of time-independent computation. Preemptive solution convergence. In select cases, solutions emerged before complete input conditions were specified. One experiment involved a quantum algorithm designed to solve a complex optimization problem, and the solution appeared in the output log before all parameters were fully entered, implying an internal quantum state evolution independent of classical input constraints. Such findings have raised profound questions. Are we observing a new emergent property of quantum systems at this scale? Could this be an undetected form of quantum entanglement, one that extends beyond known locality constraints? In an effort to explain these anomalies, physicists have proposed several hypotheses. Enhanced quantum sampling. One interpretation suggests that the 1000-qubit Majorana system is capable of an advanced form of probabilistic sampling across the Hilbert space so effectively that it can predict outcomes by extrapolating hidden patterns within input parameters. This would resemble a hyper-optimized version of Bayesian inference, where the quantum state collapses to the most statistically probable outcome before all classical information is fully processed. Quantum time symmetry. Another hypothesis posits that the system is leveraging retrocausality, concept in quantum mechanics where future states influence past states. While still speculative, some interpretations of the Wheeler-Feynman absorber theory and weak measurements in quantum mechanics suggest that quantum information could, under extreme conditions, be exchanged bidirectionally across time constraints. Multiversal computation. The most radical proposition suggests that the chip is effectively sampling solutions from parallel quantum states. In this framework, the system doesn't merely process information, it selects from pre-existing probabilities across multiple realities. This interpretation, while highly controversial, aligns with aspects of the many worlds interpretation, which posits that all possible outcomes exist simultaneously in a superposition until observation collapses reality into one definitive state. The implications of these behaviors extend beyond theoretical physics. If the chip is engaging in a form of multiversal computation, ethical questions arise, such as data integrity and historical consistency. If computational processes can retroactively modify prior inputs, how do we define objective reality in the context of quantum processing? Predictive power versus determinism. If the system appears to anticipate solutions ahead of time, does this suggest a deterministic undercurrent to the universe, contradicting our understanding of free will and quantum randomness? Security risks. If quantum computers reach the point where they can predict cryptographic keys or financial shifts with extreme accuracy, what regulatory structures must be put in place to prevent misuse? Governments and scientific institutions are already taking precautions. The U.S. Department of Energy has proposed classifying high-qubit Majorana research under national security protections, citing potential geopolitical consequences. The European Union has pushed for quantum ethics committees to oversee developments, while China has announced parallel research efforts to validate or debunk claims surrounding computational anomalies. With so much at stake, the scientific community is at a crossroads. Some advocate for immediate expansion of Majorana research, arguing that these anomalies could unlock fundamental secrets about the universe, while others call for a cautious moratorium, warning that proceeding without full understanding could lead to unintended consequences. Key questions remain: can these anomalies be reliably reproduced and explained without a clear framework to interpret results? Further research could either demystify or deepen the uncertainty. Are there hidden variables at play? Could yet undiscovered principles of quantum mechanics be at work, influencing results in ways we don't yet comprehend? Should there be global oversight? If quantum computing is nearing a tipping point, does humanity require an international regulatory framework similar to nuclear research? The Majorana 1000-Qubit quantum chip has launched us into an uncharted domain of physics and computation. Whether it proves to be the gateway to a new technological epoch or a harbinger of unsustainable complexity remains to be seen, but one thing is clear: the quantum age is no longer speculative. It is here, and it is evolving in ways we are only beginning to understand. The new state of matter that Microsoft is referring to is called a topological superconductor. It's a highly exotic phase of matter that supports Majorana fermion particles that are their own antiparticles. This unique property makes them ideal for creating topological qubits, which are significantly more stable than traditional qubits used in quantum computing. What makes topological superconductors special? Topological protection. Unlike regular superconductors, topological superconductors have special quantum states that are resistant to small disturbances, such as thermal noise or electromagnetic interference. This makes quantum computations more stable. Majorana zero modes. These are special quasiparticles that emerge in topological superconductors. They are theorized to be incredibly robust against decoherence, meaning they can hold quantum information much longer than traditional qubits. Non-abelian neons. The underlying physics of these materials allows for a type of quantum computation where information is stored in a way that is not easily disrupted by environmental factors. This enables fault-tolerant quantum computing, a major goal in the field. Why is this a big deal? Traditional quantum computers struggle with decoherence, where quantum states collapse due to outside interference. By using topological superconductors, Microsoft is trying to build quantum computers that are inherently more stable and scalable. If successful, this could be a breakthrough that brings practical quantum computing closer to reality. Topological superconductors equal superhighways for quantum information. Imagine a traditional quantum computer as a high-speed race car on a winding, bumpy road. The car, your quantum information, is extremely fast, but the bumps, environmental disturbances like temperature or electromagnetic interference, make it hard to maintain the car's speed. The car could lose control, decoherence, and you might lose the race, lose the quantum information. Now, imagine a topological superconductor as a perfectly smooth superhighway. The road has special features that allow the car, the quantum information, to stay perfectly stable, even when there are obstacles. The highway is designed in such a way that the car can handle bumps and curves without losing control. This means the car can keep going fast and not lose its path, which is exactly what we want for quantum computing. The information stays stable even in less than ideal conditions. Majorana fermions? They're the unbeatable passengers in this analogy, like passengers in the car who are their own bodyguards. Protect the car from external forces. These passengers have a unique power. They can help the car avoid obstacles and keep it on the road, even if things go wrong. They're incredibly special because, unlike regular passenger particles, they are both the driver and the bodyguard at the same time. What does this mean for quantum computers? Normally, a quantum computer needs to keep its quantum bits, qubits, in a special state, like spinning or being in multiple positions, to perform calculations. But if these qubits interact with the environment too much, they collapse, decohere, and you lose the information. With topological superconductors, the Majorana fermions ensure that the qubits are more resilient to these disruptions. In other words, the quantum information can stay safe even when things get messy around it, like the race car staying on track despite all the challenges. Big implication: this breakthrough could lead to quantum computers that can perform complex calculations without the constant threat of information loss. They would be much more scalable, able to handle more qubits, and practically usable for real-world applications like cryptography, AI, and drug discovery. What do you think? Will Majorana qubits be the breakthrough that finally unlocks practical quantum computing? Let me know in the comments, and if you're curious about how quantum mechanics is reshaping our future, check out this next video, Point to Screen. It's a deep dive into the weirdest quantum experiments blowing scientists' minds.